Welcome back to the G Lab. This is G video number 2 in the Forms of Energy series. Last video we talked about kinetic energies and all the different forms of kinetic energy. This time we're moving on from the energies of motion to potential energies, which are energies that are stored up. So maybe someone has told you, you have such potential. Can't you live up to your potential? That means that you could do something, but right now you're not. It's not usually a good sign when people say that. So potential energies are essentially energies that aren't really doing anything right now, but they have the potential to do so. They could do something. So we're going to start with a very simple one of this potential stored up energies. And we're going to start with what's called gravitational potential energy. Gravitational potential energy is basically the energy that something has because of its position above the Earth. In other words, the higher it is, the more gravitational potential energy it has. So, for instance, if you were to lift a book up onto a shelf, you've used your energy, you've used some mechanical energy to move it up there, the energy of motion there, but you've put it up high and then you stored it up on that shelf. It has the potential to fall off that shelf. It has the potential to cause some change when it lands on someone's head. But it hasn't done that yet. So it is only containing gravitational energy because it is up high, and that's the key. The higher something is, the more gravitational potential energy it has. And obviously the more mass that object has, for instance, a bowling ball on a shelf is going to have more gravitational energy than a tennis ball on a shelf, or a BB on a shelf. They all have the same height, but the more mass it has, obviously, the more change it can cause, and therefore the more energy. So when you see this logo fall here, gravitational energy, it has lots of gravitational energy when it's up high. There's a bit left as it's falling right about there, and then as it's on the ground, once it's on the ground, it has no potential energy left. There's no more potential for it to fall any further, unless you dig a hole next to it, and then it could fall into the hole. But the idea is that the higher an object is, the more gravitational energy it has. Now, oftentimes, students get confused and they think, oh, gravitational energy, that means falling because gravity makes you fall. Well, the falling part of this is the mechanical energy. That's the movement. That's the kinetic energy part of it. We're talking about the potential. So gravitational energy is not falling. Gravitational energy is not the same thing. Gravity does cause you to fall. But things have gravitational energy because it's a potential energy. It's stored up. And the key word there is up. The higher something is, the more gravitational energy it has. It doesn't have to be moving to have gravitational energy. It can just be sitting there up high. And that's when it has the most gravitational energy, because it's a form of potential energy stored up because of its position above the Earth. Next up is elastic energy. And elastic energy is the energy of basically things that are stretchy. Okay, good definition. But if you think of a rubber band, if you stretch a rubber band, you have used your energy, some mechanical energy, to store up that energy in the rubber band. And if you just hold it, it's not going to do anything. It has the potential to accidentally slip off your fingers, fly across the classroom and hit your teacher. But it hasn't done that yet. It's stored up that energy in the elastic and that stretchiness. So classic example would be a spring, for instance. And a spring, you can do a couple different things with it. You can push it and you can pull it. So when you push that spring, when you push or if you push, say, a bouncy ball or a squishy object, what you're doing is you're compressing it. So there's compressed spring. And then the other option, I guess, is if you stretch out a spring, or you stretch out a rubber band, or you stretch out a balloon, or you stretch out any kind of elastic object, then you have stretched that and it will return back to its original shape when you let go. So again, you've stored up some energy in doing that. Golf balls. Now, golf balls bounce pretty high, and we did the example in class that golf balls bounce extremely high, and the reason is because they're engineered to do so. And they don't seem like they compress all that much. They don't compress very much really at all unless you hit it with a golf club and you swing, if you're swinging 150 miles an hour and you hit that thing with the golf club, it will actually compress, it will actually squish, and then rebound off that and bounce off the head of the club. More than you think, definitely more than you think. Definitely engineered to go farther than you would, you'd be able to hit a rock, for instance, like back in the old days. When I was a kid, all we had was rocks and sticks, and that was golf. These days, so much better because golf balls have elastic energy. All right, chemical energy, our third type of potential energy here. Energy can be stored in the chemical bonds that hold things together. So chemical bonds, of course, are where atoms are attracted to each other and are held together by chemical bonds. And when you break those by having a chemical reaction, oftentimes they give off tremendous amounts of energy. So for instance, if you have some gasoline or some sort of a fuel that you can burn, or if you have food that you can burn in your body, or a log that you can burn in your wood stove or on a campfire, all of these things have a tremendous amount of chemical energy stored in them. And when you burn, say, some fuel, like say some gasoline or a piece of wood, when you actually light these things on fire, the chemicals that are holding those things together, generally a bunch of hydrogen and a bunch of carbon is what these things are made out of. When you light those, the chemical bonds between the carbon and the hydrogen are broken, and they interact with the oxygen in the air, because in order to burn these fuels, you need to have some oxygen. And what they interact with those oxygen molecules that are in the air and produce a tremendous amount of heat. Now, what they do is then rearrange those atoms. The carbon from the fuel here bonds with some of those oxygen to form CO2, carbon dioxide, and that's given off as a byproduct. It also, some of the hydrogen in these guys bonds with the oxygen in the air and forms, let's see, some H's and some O's, H2O, forms some water, and water is given off as a byproduct. And so what you end up with is a bunch of energy, and you've then rearranged the carbon and hydrogen and the oxygen atoms in the air. You've rearranged all those, and it gives off a bunch of energy. It's a chemical reaction. Same thing actually happens when you eat a piece of food. So if you eat an apple, you are putting the same kind of thing, hydrogen and carbon and some oxygen in the form of sugar, basically into your body. Your body then breathes in oxygen, just like these guys over here need oxygen. We need oxygen, so we have fuel plus oxygen, and your body then produces energy for itself. It produces energy in the form of thermal energy to keep your body warm, produces energy in the form of mechanical energy because you're moving around, and it uses the same basic process that you would have in combustion when you're burning things happens in your digestion. Your metabolism essentially breaks down the fuel and burns it for energy. And amazingly, you give off the same exact stuff. You've got fuel plus oxygen, and then you give off carbon dioxide, just like these guys do, and water. When you breathe out, you're breathing out water vapor as well. Same exact process. One other example of chemical energy that is commonly found around the house is a battery. The battery itself isn't giving off any electrical energy yet. There's nothing moving here. We've stored up the energy inside the battery in some chemicals, and it's that acid inside that is a chemical that basically stores the energy inside, and it's not released until you actually complete a circuit and allow those electrons to start flowing. So if you're looking at all these objects here, essentially the easiest way to remember what chemical energy is it's some sort of fuel. Fuel for a vehicle, fuel for your wood stove, fuel for your body, fuel for an electronic gadget. Chemical energy is stored up fuel that is then released by some sort of, usually a chemical reaction then that happens. All right, we're on to our last form of energy, and this is nuclear energy. And nuclear energy is all around us, but yet it's also kind of rare. It's a potential energy in that it's something that's stored up and has the potential to do something, and then when it does do something, wow, it gives off a lot of heat and energy. So there are two kinds of nuclear energy. There's nuclear fission, and there's nuclear fusion. So nuclear fission is where you've got an enormously large atom, like say uranium is a classic example. Here's the nucleus of the uranium atom. It has obviously a bunch of electrons flying around the outside that aren't pictured here. This nucleus of the atom, nuclear, ooh, that sounds like they could have something in common. So the nucleus is not very stable, especially when you add in an extra neutron here. And the nucleus becomes very unstable and actually breaks apart into two different atoms. You have krypton and a barium that come flying off, and a huge amount of energy is released, enormous amount of heat. And also 3 little neutrons. Now, where can these neutrons go? Well, if you've got a big chunk of uranium, I bet you there's another uranium atom right nearby. And what would one of these neutrons do when it hits it? Make it extremely unstable. And you've got nuclear fission, huge amounts of energy. And that one then releases 3 more, which affects 3 more, which those each affect 3 more. And you have a chain reaction that occurs. And you have a massive fission reaction, nuclear energy in the form of fission. Fusion is kind of the opposite process, is where 2 atoms actually fuse together. Here you have a hydrogen atom and another hydrogen atom. They look a little different. They're what are called isotopes of hydrogen. But you've got a proton here and a proton here. When these things fuse together, like they might in the sun, for instance, where you've got incredible heat and pressure, it's enough to fuse these 2 atoms together, and now you have a new atom that has 2 protons. Not very stable, so what happens is 1 neutron comes flying off, but you still have those 2 protons, and now it's not hydrogen anymore. You now have helium and a massive amount of energy coming off. So fusion and fission, kind of the opposite of each other, but they're both nuclear energy because they involve changes to the nucleus of an atom. And nuclear energy is generally found in really only about 3 places where there's a lot of nuclear energy. There are other places that have a little bit of nuclear energy, for instance, you and I. Bananas have a little bit of potassium that it's giving off, a little bit of radiation, not enough to hurt you. You'd have to eat thousands of bananas every day to even see any kind of effect. But appreciable amounts of nuclear energy, here's one right here, the sun, or any star, of which the sun is just one of billions. So stars have massive amounts of nuclear energy inside. Nuclear fusion is happening in here, and it's taking hydrogen atoms and fusing them together into helium atoms, and it gives off huge amounts of energy. It's also cooking up even bigger elements, not just hydrogen and helium, the first 2 on the periodic table. When helium gets together with another helium and those fuse together, now all of a sudden you've got 4 protons in the nucleus, and now you've got beryllium, which is number 4 on the periodic table. Or if you get a helium mixing together with a hydrogen, 2 plus 1, that gives you 3, and that gives you lithium, which is number 3 on the periodic table. So essentially you're cooking up all the elements inside these big stars, and eventually they get ejected out of these stars when the stars get to the end of their life. Pretty amazing factories of elements. Other places where nuclear energy, of course, is a nuclear bomb, is a massive release of energy. It's a chain reaction essentially that just goes like crazy until all the uranium nuclei are used up and have changed into other elements. So nuclear bomb, of course, very destructive and hard to control. But if you can actually control that nuclear fission that's occurring, you can actually harness that to make water into steam, and that steam can spin a turbine and produce electricity in a nuclear power plant. And if you look at the nuclear power plant here, you can see all the steam coming out of the cooling tower. This here there's no pollution here. There's not really any pollutants in here. It's just steam, and there's not even any carbon dioxide because you don't need. It's not like burning chemical fuel. It's not like burning coal or oil or natural gas. There's no carbon dioxide here to lead to global climate change, which is kind of nice. Of course, there's some other problems like what do you do with the spent nuclear fuel because it's still radioactive. And so even though it's very clean for the atmosphere, you then have all this nuclear fuel that you've got to somehow dispose of. And right now, generally what we do is bury that in the ground in these giant lead containers and try and keep it as tucked away from everyone as possible in these remote locations. So it's a long-term storage problem that can last thousands of years. Other places where you might see nuclear power being used is essentially in a nuclear power plant that is in a nuclear submarine. So there are nuclear powered submarines, which are pretty handy because it's kind of nice to be able to go run these things off of nuclear power that can last for a long time. Not to mention there's not a lot of oxygen down underneath the ocean. You'd have to bring that with you if it was powered conventionally with the burning fossil fuels that needs oxygen to combust. So pretty handy for a nuclear submarine. These things can go for years actually on the little bit of fuel that they have. Of course, they have to come up to get air, and so people can go shopping and all that kind of stuff. Other places you might find a tiny little nuclear power plant is in satellites, or not satellites actually, but deep space missions. Like here's the Cassini spacecraft that went to Saturn to go check out Saturn for quite a while, and this here, of course, is too far away from the sun to really have very useful solar panels there. And so what they did is they put a little tiny chunk of radioactive material in there, and it's enough to give this thing electricity for years and years and years. And that's another use of nuclear energy. It's essentially just a little tiny power plant. So basically, sun or other stars, nuclear explosions, and then nuclear power plants, either large or small, to take these to remote places that it's hard to get fuel, and maybe there's not a lot of oxygen to support normal combustion. So there you have it. There's our forms of potential energy, the energy of storing things up, whether that's because of elasticity or gravity or chemical reactions or the energy stored in the nucleus of an atom. Potential energies are energies that are stored.